All right, hey there. So in this video, we're going to do some example derivations using universal derivation, the new derivation technique we just talked about. There's 3 example problems here, and these are on page 33 of slideshow number 17. So for the first one, let's take a look here. I've got the premises already written down and the conclusion here. And the thing to note is that our show line has as its main connective a universal quantifier. And that means we can do universal derivation. So universal derivation, like conditional and indirect derivation, allows us to cancel a show line by showing, in fact, something else. But unlike conditional and indirect derivation, there's no assumption. So with conditional and indirect, we have a show line, an assumption, and another show line. With universal, we just go straight to the second show line. What we write down is we write down show, and then the formula that we're trying to show is the exact formula that was above, but with the quantifier removed and the variable that was bound, that is x in this case, replaced with a new constant. In this case, there are no constants, so we can use a, and so we're going to try to show GA arrow FA. And universal derivation says if we can show that in line 4, then we've shown line 3, because a is arbitrary here. If we can show for any arbitrary thing a that GA arrow FA is true of it, then we've really just shown that for anything GX arrow FX is true of it. Okay, so how should we proceed now in line 4? Well, we've got a conditional and our show line. So just as we know from sentential derivations, we're going to do conditional derivation. Here we assume the antecedent and we try to show the consequent, in this case, FA. Okay, so how are we going to show FA here? Well, first we're going to get rid of the quantifiers in lines 1 and 2, and then finish our proof. So in line 1, I'm going to get rid of the universal quantifier and replace the x with an a. So I'm going to get if GA, then not MA, that comes from line 1 by universal out. Now from line 5 and 7, we can get not MA, that comes from arrow out. In line 2, we can do universal out and make this FA or MA. That comes from line 2 by universal out. And finally, getting a little bit closer to this proof than I wanted to, so I'm going to put a little line there just to make sure we don't get confused here. This is a totally different proof here, so just imagine that space is a little bit bigger there. From lines 8 and 9, I hope you can see that we can get FA. That follows from lines 8 and 9 by or out. Okay, so let's see what happened. Did we show FA? Yeah, we did. There it is at the bottom of our proof. That's a direct derivation. Box and cancel. Now, after assuming GA, we showed FA. That means we've conditionally derived if GA, then FA. But if we showed if GA, then FA for an arbitrary A, as we did, that's just what it is to show that everything that you pick, if it's G, then it's F. That is, universal derivation tells us that's sufficient to cancel this line. And so, whoops, we cancel it and we box. And there we go. There's our first universal derivation. Again, I'm just going to sort of, I don't know if I have a piece of paper here, I'm just going to sort of try to hide this stuff here. Not ignoring that, there's our first universal derivation example. Okay, let's try this one here. Again, ignoring the stuff above it now. No, I don't have a piece of paper. Okay, so we've got 2 premises, and we've got our show line here. And the important thing to note here is that, again, our show line is a universally quantified formula. The main connective is a universal. So that means we can do universal derivation. And what we do is we immediately write a show line where we take off the quantifier and replace the variable, in this case x, with a new constant. Here, though, we have to be careful because A and B have already been used. So we go to the next available constant, c, and write GC. What this is going to do is this is going to ensure that it wasn't any special information we had about A and B, that they have property F, that allows us to show this. Rather, for anything, even if we don't know anything about it, like C, we could show that it's not G. So let's see how we proceed here. First, I'm going to do universal out with line 1. That's going to let me get this X to be whatever I want. I'm going to make it C because I'm going to hopefully try to get not GC in some way. So we go GC arrow negation existential quantifier FY. That comes from line 1 by universal out. And again, we can do that because there's no restrictions on universal out. So even though C is not a new constant in line 5, it's still fine to do. And what do we do now? Here's a sort of a tricky situation. First, I'm going to break up line 2. Doesn't matter which side I get, I'll just take FA in this case. That comes from line 1 by and out. And now notice, if I know that A has property F, then I know that something has property F. That is, I know that there is a Y, Fy. I could have made that X or Z, but I wanted to do Y so it matches what's up here in line 5. That comes from line 6 by existential in, a rule we've seen earlier. Now I'm almost in a position to do arrow out the modus tollens version, but I need to have the negation of the consequent in line 5. So I need to double negate this. So I'll go not existential y fy. That comes from line 7 by dn. And now I've got the negation of the consequent. So arrow out says I can get the negation of the antecedent, which is not gc. That comes from line 5 and 8 by arrow out. And that's good because that's what we were trying to show. So we've directly derived not GC, so we box and cancel. And because C was arbitrary, that's enough to show that the universal formula is true by UD. So we box and cancel. All right, one more example problem I'd like to do here. So let me turn the page. And this is the last one on page 33. Let's make sure, there we go. Can we see that okay? Good. All right, so we've got two premises and a conclusion. And again, you should notice that the conclusion is a universally quantified formula. So we can do universal derivation. And again, we do this by writing a show line, taking off the quantifier, and replacing the variable that was quantified with a new constant. Again, there's no constants yet used, so we can use A in this case. Okay. What do we do now? Well, I've got a negated existential here. So the first thing I'm going to do is do my not existential out rule. Oh, actually, I'm not going to do that actually in this case. That's something you could do, but in this case, we're not going to need to do that. Not right away anyway. Okay, let's do line 1. Universally quantified formula. We're going to do universal out, and that's going to give us FA biconditional not GA. We replace every occurrence of X with whatever name we want, and in this case we're going to do A. That comes from 1 by universal out. Okay, what are we going to do now? Well, we want to turn this biconditional into a regular conditional, and we can choose which direction. We can either get FA arrow not GA or not GA arrow FA. I'm going to do the second one because that's going to be the most useful in getting what we want, which is FA. That is, I'm going to transform this in line 5 to this conditional in line 6. That comes from line 5 by our biconditional out rule. Now, if we had not GA, we could get FA, which is what we're looking for. And we can. To do that, we have to do something with line 2 that I mentioned a second ago, but didn't go into. We have to use what we call our not existential out rule. We haven't actually introduced this rule yet. You'll see it on your handout, and in the next couple of videos we'll describe it. But just to, what it essentially lets us do is it lets us move a negation past an existential quantifier as long as we switch the quantifier to a universal. So again, we haven't talked about this rule yet. We've got another video about it online. But here's what the rule lets us do. It comes from line 2, and we call this not existential out. And again, that should be familiar to you from the translations we did in the last section, section 2 of this class. Now, we can do universal out to make this x anything we want. We're going to choose A, not GA. That comes from line 7 by universal out. And we finish our proof by doing an arrow out with 6 and 8 to get FA. So that's 6 and 8 by arrow out. We were trying to show FA, and we did. And given universal derivation, that's sufficient to show by UD that everything is F. All right, hope these are helpful. Definitely do some practice problems on your own, and let me know if you have any questions.